All right, everyone. Hopefully you are having a fantastic evening. We're going to be taking a look at the study guide and the solutions therefore, um, going into our Unit 5 test tomorrow. I'm actually going to start things off on number 3 here, mostly because number 3, the process through which we will do number 3, is going to be similar to how we do number 1. Now for number 3, we are not number 1, but number 2. Now for number 3, we're asked to find each of sine of 7 pi over 12, cosine of 7 pi over 12, and tangent of 7 pi over 12. I'm going to demonstrate how to do this for one of these, and leave it as a bit of an exercise to the reader in order to kind of fill in the gaps from there, but should not be too horribly difficult. Let's take a look at cosine of 17 pi over 12, and in particular we are asked to use the sum and difference formulas in order to do so. So we could try to use half angle here. There wouldn't be anything necessarily wrong with that, but in this case we are specifically being asked to use sum and difference. So let's take a look at how we would do that. So cosine of a sum of two angles. This is cosine of some kind of alpha plus some kind of beta. Cosine is mean, so cosine is going to group kind of the cosines together, group the sines together, and it's going to have shenanigans occur with the plus to the minus. And so because of that, this is going to be cosine of alpha times cosine of beta minus sine of alpha sine of beta. So the only thing that we really need to do here is figure out what would the alpha and beta need to be such that when the two get added together, they equal 17 pi over 12. And in particular, what would they need to be such that we actually know what cosine and sine of this alpha and beta would be for when we do this kind of conversion. My advice when we are working with radians, with degrees it's not too horrible, and certainly we could take a stab at this problem by trying to convert everything into degrees. That would be totally fine. But my approach for dealing with this in terms of radians is we're just going to set that first angle, that first alpha, to be pi over 4. In order for us to be able to even approach this style of problem directly, it needs to be able to be decomposed into pi over 4 plus something. So the only thing that we're really missing here is what is beta, but we know that alpha plus beta, or in particular here that pi over 4 plus beta, needs to equal 17 pi over 12. And so subtracting pi over 4 from both sides, I get that beta is 17 pi over 12 minus pi over 4. Clean that up a little bit. Pi over 4, when we're subtracting from 17 pi over 12, maybe a better way or an easier way to write this is we are going to be subtracting 3 pi over 12, which is going to be the same as 14 pi over 12, which is equal to 7 pi over 6, an angle that we in fact know. And so the beta here, if alpha is equal to pi over 4, the beta here would be 7 pi over 6. And so we get that this sum is going to be, well, it's cosine of pi over 4 plus 7 pi over 6, which should be equal to cosine of pi over 4 times cosine of 7 pi over 6 minus sine of pi over 4 times sine of 7 pi over 6. Cosine of pi over 4, that's going to be unit circle knowledge. This is just root 2 over 2. Cosine of 7 pi over 6, negative root 3 over 2. This is a quadrant 3 angle. And we are subtracting root 2 over 2 times negative 1/2. We could be done here, but I'm going to keep going. This is negative root 6 plus root 2, all divided by 4. All right, for number 4, we are approaching sum and difference still, but we're kind of doing it from a slightly different perspective. In this case, this is sine of pi over 12 times cosine of pi over 4 minus sine of pi over 4 times cosine of pi over 12. If we look here, notice how we have a mixture of sines and cosines. So think in this case, sine and cosine getting along. That means the one in charge is going to be nice. We are going to collapse this into some kind of sign of a plus b or a minus b. In this case, we know that this is going to be a minus b because sine isn't going to do anything shady with that plus. This right here is our alpha. This right here is our beta. And so we end up with, this is going to be sine of alpha minus beta, which is equal to sine of pi over 12 minus pi over 4. Matching the denominators, doing out the subtraction, this is going to be sine of negative pi over 6. A couple of different ways that we could evaluate this. One is that we could use the even and odd properties. That would be totally fine. Also, negative pi over 6 is in quadrant 4. That's a quadrant 4 angle. And the reference angle of pi over 6 is going to give us a value of 1/2. Sine is negative in quadrant 4. And so our answer here is just negative 1/2. One more in terms of our sum and difference. This is cosine of the arctan of negative 12 over 5 minus arc cosine of negative 4 over 5. So remember, we're dealing with these inverse trig functions like this. My advice has, generally speaking, been to just leave this as simply as we can. We'll go ahead and reframe this. This is cosine of alpha minus beta, where alpha is just equal to arctangent of negative 12 over 5, and beta is equal to arc cosine of negative 4 over 5. And cosine of alpha plus beta, minus beta, we know that this is going to be mean. Cosines are going to be grouped, and that minus is going to flip-flop. All right, let's reframe. We're kind of not set up well to think about things in terms of their inverse function, in terms of our inverse functions here. And so reframing this alpha equals arctan statement to say that tangent of alpha should equal negative 12 over 5. And the additional piece of information we have here is that alpha must be a quadrant 4 angle, because that is what the inverse trig function for tangent tells us, is that if we have a negative value, normally it would either be in quadrant 2 or 4, but for inverse tangent, always, always, always going to be in quadrant 4. Likewise, cosine of beta is going to be equal to negative 4 over 5, where beta lives in quadrant 2. Similar logic. This is just always the case for the inverse cosine of a negative value. It's either quadrant 1 or 2. The fact that it is negative tells us quadrant 2. This gives us two pieces of triangle information. Draw triangles, which I clearly cannot. We'll call this alpha, where tangent is opposite over adjacent. Fill in the hypotenuse, since this is one of our special triangles. And cosine is a 3, 4, 5 triangle. This is beta. This is 4. This is 5. This is 3. So cosine of alpha should be equal to adjacent over hypotenuse is going to be 5 over 13, where we are in quadrant 4, so this will be positive because cosine is positive in quadrant 4. Cosine of beta, that should say beta, not alpha. We already know what that is. That is negative 4 over 5. And then plus sine of alpha, that's going to be opposite over hypotenuse. That is 12 over 13, and it will be negative because sine is negative in quadrant 4. And sine of beta, 3 over 5, positive because sine is positive in quadrant 2. And so we end up with negative 20 over 65 minus 30. This is negative 56 over 65. Clean that up a little bit. Negative 56 over 65. All right, let's take a look at number 6. In this case, we are told that sine of theta is equal to negative 8 over 15. That was supposed to be 8 over 17. Apologies with that. I was trying for a Pythagorean triple and then messed up, switched my hypotenuse here. And we are told that theta lives between pi and 3 pi over 2, which means that theta is a quadrant 3 angle. And we are trying to find cosine of 2 theta. Now, there are a couple of different ways that we can do this, but the one that I would use is I would decompose this into cosine squared of theta minus sine squared of theta. So the only thing we really need to find here is cosine squared of theta. If sine of theta is equal to negative 8 over 15, this is our we would say our opposite side. This is our hypotenuse. 225 minus 64 is going to be 161. I get that this is the square root of 161. A little bit messy. Again, apologies about that. This is our theta here. And so cosine squared of theta, rather cosine of theta, square root of 161 over 15. And cosine squared of theta minus sine squared of theta will be the same as, you could write it this way, square root of 161 over 15 squared minus, we'll say negative 8 over 15 squared, noting that this is, of course, negative because we are in quadrant 3, although ultimately for this problem it doesn't really matter because we are going to square both. And this is honestly totally fine as our answer. All right, taking a look at number 7. We are told that cosine of theta is equal to negative 24 over 25, where theta lives in the second quadrant, and we are trying to find tangent of theta over 2. Actually, I'm going to write this out. This is that we are between pi over 2 and pi. We'll see why I did that later. So tangent of theta over 2, there are a couple of formulas you can use. I am going to, again, default to the one that is maybe not the most basic, but the one that we kind of focused on most. This is 1 minus cosine of theta over 1 plus cosine of theta. And the good news here is we actually already know what cosine of theta is going to be. This is going to be plus or minus the square root of 1 minus 24 over 25 over 1 plus 24 over 25. That will certainly simplify. Actually, it simplifies down quite a bit. I believe that ends up being like 1/7. Double check me on that. I believe that's right. And so now the only thing that we have left to resolve is the plus or minus. Recall that to resolve the plus or minus, we need to figure out where theta over 2 lives. We know where theta lives. We need to know where theta over 2 lives. The way we do this is if theta lives between pi over 2 and pi, then theta over 2, very similar to kind of what we do with our solving process, must live between pi divided by 2 and pi over 2 divided by 2, which is pi over 4. This is just dividing everything by 2, or multiplying everything by 1/2 is maybe a better way to think about it. Where is pi over 4 to pi over 2? Well, that is going to be a quadrant 1 angle where tangent is positive. And so our final answer here is going to be positive 1/7. All right. Taking a look at number 8 here, we are trying to figure out all of the theta that live between 0 and 2 pi. This is kind of our normal parameter here. Such that 8 sine of theta is equal to 4 sine of theta minus 2 root 3. So our strategies here, we don't really actually have all that many options here. This is very similar to the second example that we did when working through 5.5 on that first day. So I need to get all of my thetas on one side. Best way to do that here, dividing everything by sine of theta is not going to be super effective because of this minus 2 root 3 term. But also that's already just a fairly risky kind of venture. I'm not really going to be dividing by trig functions just because you have to be pretty careful when you do so. And so I'm going to avoid all of that. Instead, subtracting 4 sine of theta over to the other side, which gives me that 4 sine of theta is equal to negative 2 root 3. Again, solving here, dividing both sides by 4, I get that sine of theta is equal to negative root 3 over 2. There are 2 different quadrants where sine is going to be negative. That'll either be in quadrant 3 or in quadrant 4. Pi over 3 is my reference angle. That gives me root 3 over 2. And so I'm looking at 4 pi over 3 as one and 5 pi over 3 as my other node. Technically, yes, we would have this plus 2 pi k, which is the thing that kind of takes into account our possible coterminal angles. But because theta has to be between 0 and 2 pi, you can check this yourself. Any k value other than 0 is not going to cut it. We would not end up needing to look for coterminal angles. And so our 2 solutions, 4 pi over 3 and 5 pi over 3. Take a look at number 9 here. This is sine of theta times cosine of theta is equal to negative cosine of theta. Same constraint on theta, that theta lives between 0 and 2 pi. So here's one where we could probably actually get away with dividing both sides by cosine of theta if we were then very careful and made sure that, in fact, we were not losing solutions there. But again, I'm going to try and keep things relatively simple. I don't want to worry about that. Instead, for these efforts of getting all of our thetas onto one side of the equation, adding cosine of theta to both sides, I get sine of theta times cosine of theta plus cosine of theta is equal to 0. Needing to rewrite this in terms of multiplication so that I can use the zero product property. factoring out a cosine of theta here. And in doing so, I get that cosine of theta equals 0, and that sine of theta plus 1 equals 0, which is akin to saying that sine of theta is equal to -1. The thetas that I get from cosine of theta equaling 0 are either pi over 2 and 3 pi over 2. Wow, that pi got away from me. 2 pi, okay? And the theta that I get from sine being equal to -1 is actually also 3 pi over 2. But because there's overlap, we don't really need to consider that. So, not that it's like wrong, but obviously, if we have our solution from the second node here, then it will provide us also a solution from the third node. And again here, the only k value that matters is k equals 0 because of these constraints. And so we have two solutions here, pi over 2 and 3 pi over 2. Where technically 3 pi over 2 is kind of like a double solution, which doesn't really have meaning for us. It's just a solution. All right. Taking a look at number 10 here. This is tangent of 3 theta is equal to root 3. Again, standard constraint on theta. Here we're actually going to see this mattering. Well, we saw it mattering before. It was why k was equal to 0 for all the others. But here we're actually going to need to mess with the constraint here. My advice when we have this kind of 3 theta here and there aren't other kind of angles to get in the way is we are going to do this u substitution thing. We'll say that u is equal to 3 theta and allow us to rewrite this as tangent of u is equal to root 3, just kind of setting aside the complexity, noting here that u must live between 0 and 6 pi, which is just taking the upper bound and lower bound, multiplying them by 3. All right, tangent is going to be positive in the first quadrant and the third quadrant. You can check the unit circle angles that would work for this. But I happen to know that this is going to be pi over 3. Yep. Plus 2 pi k. And 4 pi over 3, since we're in quadrant 3, plus 2 pi k. And so checking our values of k. Oh, before we do that, let's adjust our constraints so that we know when to stop. 6 pi here. Maybe a better way to write this is like 18 pi over 3, just to kind of give us an indicator of when we've gone too far. We're going to check our k values. For k equals 0, we get pi over 3 and 5 pi over 3 for our value of u. Each time we increase k by 1, we're going to add 2 pi here. But a more convenient way to think about adding 2 pi here would be adding 6 pi over 3. So 6 pi over 3 plus our node for pi over 3 is going to be 7 pi over 3. Adding 6 pi over 3 here, we get 11 pi over 3. Same deal, increase by 1, add by 6 pi over 3. That's 13 pi over 3 and 17 pi over 3. And we're really, really close to our boundary, but let's go ahead and check. For k equals 3, we get, that's going to be 19 pi over 3 and 23 pi over 3, which are both larger than 18 pi over 3, which is why we set it up as 18 pi over 3 to kind of catch very, very quickly when we are good. So these are our values for u. Of course, we are not trying to solve for u, we're trying to solve for theta. And so dividing each of these by 3 to solve for theta, I get that theta is pi over 3, 5 pi over 3, whoa, dividing them by 3, pi over 9, 5 pi over 9, 7 pi over 9, 11 pi over 9, 13 pi over 9, and 17 pi over 9. All right, one last question here. This is one that was on the that was just directly on the examples, but I did want to kind of highlight it again. This is cosine of 2 theta plus sine of theta is equal to 0. Now, unlike with number 10, where this 3 theta is the only argument that we see, notice here for number 11 that the cosine is in terms of 2 theta, the sine is just in terms of theta. That presents a little bit of an issue with regards to dealing with this particular kind of problem through that attempt at U substitution directly. And so what we're going to do instead is we're going to try and write everything in terms of just that linear theta term. We've already done this with cosine of 2 theta. This is going to become cosine squared of theta minus sine squared of theta plus sine of theta equals 0. Now, ideally, we would like to be able to write this as a product. Problem is, as things stand right now, not realistically going to be able to factor our left-hand side when it is in terms of a mix of sines and cosines. So what we're going to do here instead is we're going to rewrite cosine squared of theta. This is 1 minus sine squared of theta minus sine squared of theta plus sine of theta equals 0, for which we get 1 minus 2 sine squared of theta plus sine of theta equals 0. I'm going to do a quick little U substitution here just to make this look a little bit cleaner. And I'm going to rearrange things a little bit. This is negative 2u squared plus u plus 1 equals 0, where u is just the same as sine of theta. And then I don't like dealing with that negative in front, so dividing everything here by negative 1, I get 2u squared minus u minus 1 equals 0. Two numbers that multiply the 2 and the negative 1 here. Two numbers that multiply to make negative 2 and add to make negative 1 are going to be negative 2 and positive 1. And so doing my factoring, I get u minus 1 times 2u plus 1 equals 0. Go ahead and confirm that for yourself. U should be equal to 1, and u should be equal to negative 1/2. Which, of course, means that sine of theta should be equal to 1, and that sine of theta should be negative 1/2, for which I get that theta should be pi over 2 for my first node, and negative 1/2 is going to be, we already looked at this, this is going to be 7 pi over, maybe we actually didn't look at this one, but it will be 7 pi over 6 and 11 pi over 6, pi over 6 reference angle in quadrants 3 and 4. Yes, technically we would want to do the 2 pi k thing, but again, we are just, the only k value that works is k equals 0. So we are more than happy to just box our answer. So hopefully this makes a lot of sense. If you have any questions, of course, you are more than welcome to reach out. Hopefully you guys have a good rest of your night, and best of luck to you all tomorrow.